Welcome back to statistics. Up to this point, we've been computing confidence intervals for a mean under the assumption that the population standard deviation sigma is known. But this is usually unrealistic. After all, if you know what sigma is, then presumably you had access to the population data. And if you have all the population data, then you could just go ahead and compute mu as well, and there'd be no need for a confidence interval. So, what do we do when the population standard deviation sigma is unknown, as it is usually? We want to discuss that now, and in a subsequent video, we'll go through an example. So, let's see what's in store. So, estimating mu when sigma is unknown. As we've said, the procedures we've used up to now have assumed that sigma is known. But in most real world cases, that's not true. Both mu and sigma are unknown. Since sigma is unknown, we must estimate it from the sample data. And this additional uncertainty caused by the unknown value of sigma affects the way that critical values are computed for the confidence interval. Rather than using the standard normal distribution to calculate critical values, a new family of distributions is required, and it's called the t-distributions. So if sigma is unknown, our first job is to estimate it. And we can do that using the sample data. After all, we can compute the sample standard deviation, the standard deviation of the data in our sample, and use that as an estimate for the standard deviation in the population. This is exactly what we did in estimating the unknown mean mu, right? We used x bar as an estimate for mu. Well, now we're just piling on. In addition to using x bar as an estimate for mu, we're using the sample standard deviation s as an estimate for sigma. So how does this affect our confidence interval for mu? Well, recall the formula for the margin of error. The margin of error is a critical value times the standard deviation of x bar, where the standard deviation of x bar is sigma over root n. The fact that sigma is now unknown impacts both the critical value z star and the standard deviation of the sampling distribution. Let's first look at critical values. If sigma is unknown, the basic change is that critical values no longer come from the standard normal distribution. Rather, they come from the t-distribution with n-1 degrees of freedom. This is a distribution that's closely related to the normal distribution, but it's different. It takes into account the additional uncertainty caused by the unknown standard deviation sigma. There's this concept of the degrees of freedom for a t-distribution. In our work, the degrees of freedom for the t-distribution that we're using will always be one less than the sample size of our data. So we'll always be using t-distributions with n-1 degrees of freedom, where n is the number of observations in our sample data. Here's a plot for the t-distribution with 1 degree of freedom. That's the curve you see in red. And for comparison's sake, I've drawn the standard normal distribution with that dashed blue line. So degrees of freedom 1 would mean that you have a sample of size 2. So that's the smallest possible sample, right? And this would be the distribution that critical values would come from if you're dealing with samples of size 2. The t-distribution with 1 degree of freedom, as seen in red there. Here's the t-distribution with 3 degrees of freedom. That would correspond to samples of size 4. Again, we see that the t-distribution, shown in red, is similar to the normal distribution. But, like the case of 1 degree of freedom, The t-distribution is shorter and a bit wider than the standard normal distribution. That is, it has a greater spread. And this is true in general for t-distributions. The t-distributions have a slightly wider spread than the standard normal distribution, and this is again because of the uncertainty, the additional uncertainty caused by the unknown standard deviation sigma. Here's the t-distribution corresponding to samples of size 8, that is, the t-distribution with 7 degrees of freedom. Here we have 16 samples and a t-distribution with 15 degrees of freedom. It's getting very close to the standard normal, and this is the trend. As the sample size gets higher, the t-distributions approach the standard normal distribution. Here's samples of size 32, 31 degrees of freedom, and at samples of size 64, the t-distribution is essentially indistinguishable from the normal distribution, the standard normal distribution. Now let's look at how the standard deviation of the sampling distribution is going to be handled. If sigma is unknown, we simply don't have anything to plug in to the formula for the standard deviation of the sampling distribution. But again, what we do is we estimate our sigma with S. So we replace sigma in the standard deviation of x bar with S, the sample standard deviation. This gives us what's known as the standard error of x bar. So the standard error of x bar is our estimate for the standard deviation of the sampling distribution. What about the margin of error? Well, if you look at the formula for the margin of error when sigma is known, we're going to just make a couple of basic replacements. Instead of critical values z star from the standard normal distribution, we're going to be using critical values t star from the t distribution with n-1 degrees of freedom. And instead of the standard deviation of x bar, we're going to use the standard error of x bar. So that, in summary, are the changes that are necessary when estimating mu when sigma is unknown. We use the same point estimate for mu, that is x bar. We form a confidence interval in the same way, that is, by slapping a margin of error to the left and right of our point estimate x bar. But the margin of error is calculated a little bit differently. We use critical values from the t distribution with n-1 degrees of freedom, and we use the standard error of x bar as our estimate for the standard deviation of x bar. So you can see that the procedures are very similar when sigma is unknown, just some of the details have changed. We'll take a look and play this through in an example in our next video. In the meantime, stay safe, and we'll be back at you real soon.